In espionage movies, we see international spies with multiple passports, each claiming a different identity. However, we know that each of these passports represents the same person. The trigonometric identities act in a similar manner to multiple passports. There are many ways to represent the same trigonometric expression. Just as a spy will choose an Italian passport when traveling to Italy, we choose the identity that applies to the given scenario when solving a trigonometric equation. In this section, we'll begin an examination of the fundamental trigonometric identities, including how we verify them and how we can use them to simplify trigonometric expressions. All right. So verifying the fundamental trigonometric identities, right? Identities enable us to simplify complicated expressions. They are the basic tools of trigonometry used in solving geometric equations, just as factoring, finding common denominators, and using special formulas are the basic tools of solving algebraic equations. In fact, we use algebraic techniques constantly to simplify trigonometric expressions. Basic properties and formulas of algebra, such as the difference of squares formula and the perfect squares formula, we will simplify the work involved with trigonometric expressions and equations. We already know that all the trigonometric functions are related because they are defined in terms of the unit circle. Consequently, any trigonometric identity can be written in many ways. To verify trigonometric identities, right, we usually start with more complicated side with the more complicated side of the equation and essentially rewrite the expression until it has been transformed into the same expression as the other side of the equation. So our goal here is to make, right, both sides of the equation equal to one another, right? It doesn't have to get all the way down to the perfect um simplest form, right? It just has to be the left side has to equal the right side, and then you're good to go. Sometimes we have to factor expressions, expand expressions, find common denominators, or use other algebraic strategies to obtain the desired result. All right. In this section, we will work with the fundamental identities, the Pythagorean identities, the even odd identities, the reciprocal identities, and the quotient identities. So we will begin with the Pythagorean identities, right? As you can see here in table 1, which are equations involving trigonometric functions based on the properties of a right triangle. So we have already seen and used the first of these identities, but now we will also use additional identities. So for the Pythagorean identities, we have sine squared plus cosine squared equals 1. 1 plus cotangent squared is equal to cosecant squared. 1 plus tan squared is equal to secant squared. For us, I feel like it'll be easier to just focus on sine squared plus cosine squared equals 1, as you can use that to derive everything else. Okay. So the second and third identities can be obtained by manipulating the first. The identity 1 plus cotangent squared is equal to cosecant squared is found by rewriting the left side of the equation in terms of the sine and the cosine, right? So let's say we wanted to prove it, right? Prove that 1 plus cotangent squared is equal to cosecant squared, right? We can simply, right, change the 1 plus cosine, excuse me, we can change the cosecant squared into 1 plus cosine squared over sine squared, right? And then, right, remember, in order for you to add two fractions, you have to have the same denominator. So that being said, right, our denominators are cosine squared theta, right? And what you do to the bottom, you do to the top. So when we add those together on top, we have sine squared plus cosine squared theta which we know is 1, divided by sine squared theta, which gives us 1, which is cosecant squared theta. Boom, right? Similarly, if we have 1 plus tan squared theta is equal to secant squared theta, it can be obtained by rewriting the left side of the identity in terms of the sine and cosine. This gives us 1 plus tan squared theta is equal to 1 plus sine over cosine squared theta, right? And we just go through the same motions, right? In order for us to add fractions, we have to have the same denominator, which is dividing to the top. So cosine squared theta plus sine squared theta over cosine squared theta leads us to 1 over cosine squared theta, which is secant squared theta. All right. And that's all happened on the right-hand side. Okay. The next set of fundamental identities is the set of even-odd identities. The even-odd identities relate the value of a trigonometric function at a given angle to the value of the function at the opposite angle and determine whether that identity is odd or even. So even-odd identities, right? So here we go. We have tan of negative theta is equal to negative of tan theta. We have sine of negative theta is equal to negative sine theta, right? That's odd, right? And then we have our cosine of negative theta is equal to cosine theta, right? Again, sine, cosine, we can use that to define everything. So we should really focus on those. Recall that the odd function, right, is the one in which you place a negative value in as the input, right, for x, and then we get back out a negative y value, right, for all x in the domain of f, right? The sine function is an odd function because sine of negative theta is equal to negative sine theta. The graph of an odd function is symmetric about the origin. For example, let's consider this. Sorry about that. All right, so for example, consider the corresponding inputs of pi over 2 and negative pi over 2. The output of sine of pi over 2 is opposite the output of sine negative pi over 2. Thus, sine pi over 2, sine 90 degrees, is equal to 1, and sine of negative pi over 2 is equal to negative sine pi over 2, which is negative 1. All right. This can be verified, right, on our unit circle as well. So you can see this in figure 2 right here, right? When we're at pi over 2, our y value is 1. When we're at negative pi over 2, our y value is negative 1. So recall that an even function is one in which when we plug a negative value in for our input, we get back out a positive value for our output. So, and that's for all x in the domain of f. Right, so the graph of an even function is symmetric about the y-axis. Cosine function is an even function because cosine of negative theta is equal to cosine theta. So for example, consider the corresponding inputs pi over 4 and negative pi over 4. The output of cosine pi over 4 is the same as the output of cosine of negative pi over 4. Thus, cosine of negative pi over 4 is equal to cosine of pi over 4. And then you get that decimal approximation by, of course, typing that into the calculator. Okay. So here we go. So here's our graph of cosine, right? And you can see when we plug in pi over 4, we get 0.707 in the calculator. And also when we plug in negative pi over 4, we get the same positive 0.707, right? Thus proving that it's an even function. So for all theta in the domain of sine and cosine functions respectively, we can state the following. Since sine of negative theta is equal to negative sine theta, sine is an odd function. And since cosine of negative theta is equal to cosine theta, cosine is an even function. The other even odd identities follow from the even and odd nature of the sine and cosine function. So for example, consider the tangent identity. Tan of negative theta is equal to negative tan theta. We can interpret the tan of a negative angle as tan of negative theta is equal to sine of negative theta over cosine of negative theta, right? And remember that the sine of negative theta is going to be negative sine theta over just a positive cosine theta, and a negative divided by a positive, remember, is a negative. So this will equal negative tan theta. So tangent is therefore an odd function, which means that which means that tan of negative theta is equal to negative tan theta for all theta in the domain of the tangent function, right? So this is what I mean. We can use the sine and cosine, right, to find whatever it is that we need. We can use it to derive everything else, right? Which makes it a little bit better, a little bit easier for us, all right? Just bear with me 1 second. All right. So the cotangent identity, right? So cotangent of negative theta is equal to negative cotangent of theta. This follows from the sine and cosine identities. We can interpret the cotangent of a negative angle as cotangent of negative theta is equal to cosine of negative theta over sine of negative theta. Again, because the sine is negative, right? Cotangent will also be negative. So negative cotangent of theta, right? Cotangent is therefore an odd function, which means that cotangent of negative theta is equal to negative cotangent theta for all theta in the domain of the cotangent function. The cosecant function is the reciprocal of the sine function. This means that the cosecant of a negative angle will be interpreted as cosecant of negative theta is 1 over sine of negative theta, which is again 1 over negative sine theta, which becomes negative cosecant theta. So the cosecant function is therefore an odd function. Finally, the secant function is the reciprocal of the cosine function, and the secant of a negative angle is interpreted as secant of negative theta is equal to 1 over cosine of negative theta, which is equal to 1 over cosine theta, which is equal to the secant theta. So the secant function is therefore even, right? To sum up, only two of the trigonometric functions, cosine and secant, are even. The other four functions are odd, right? Verifying from the even odd identities. So the next set of fundamental identities is the set of reciprocal identities, right? Which, as the name implies, right, relates to trigonometric functions that are reciprocals of each other, right? So, for example, we have cosecant of theta is equal to 1 over sine theta. Secant theta is equal to 1 over cosine theta. And of course, cotangent theta is equal to 1 over tangent theta. Those are reciprocal identities. Let's look at some more. Essentially, what we're doing right now is we're building a toolbox that we can use to answer our questions. Right? So the final set of identities is the set of quotient identities, which define relationships among certain trigonometric functions and can be very helpful in verifying other identities, right? So for example, our tan theta is equal to sine theta over cosine theta. The reciprocal and quotient identities are derived from the definitions of the basic trigonometric functions, right? So basically, as long as you know the basics, you can use that information to find whatever it is you need to find. All right. Okay. Let's recap real quick. Let's recap real quick because that was a lot. All right. So I want to summarize the trigonometric identities. Okay. So once again, we have the Pythagorean identities. They're based on the properties of the right triangle. So cosine squared plus sine squared equals 1. We have the even odd identities, right, which relate the value of the trigonometric functions at a given angle to the value of the function of at the opposite angle. So sine of negative theta is equal to negative sine theta, and cosine of negative theta is equal to cosine theta. Okay. We have some more. Bear with me 1 second. Okay. So we have our reciprocal identities, of course, right? Which define the reciprocals of the trigonometric functions. Should have been these. Cosecant theta is equal to 1 over sine theta. Secant theta is equal to 1 over cosine theta. And cotangent theta is equal to 1 over tangent theta. All right. Last but not least, we have the quotient identities, right? Which define a relationship among the trigonometric functions. Tan theta is equal to sine theta over cosine theta. So let me give you guys a little T, a little how-to right here. So now, how to. So given a trigonometric identity, we want to verify that it's true. This is how you do it. Step one, work on one side of the equation. It's usually better to start with the more complicated side of the equation, right? As it's easier to simplify than to build. Two, look for opportunities to factor the expression, squared a binomial, or add fractions. Noting which functions are in the final expression. Look for opportunities to use the identities and make the properties the proper substitutions, right? Step three, if these steps do not yield the desired result, try converting all terms into sines and cosines. This I feel like is the most powerful trick that you could do, right? Or strategy is to convert all of the terms, right, to sines and cosines. Everything will work out right after that. All right. Let's go over an example. So in this example right here, right, we want to verify a trigonometric identity, right? We want to verify that tan theta cosine theta is equal to sine theta. Now, for me, right, tan theta times cosine theta, the left-hand side, is actually more complicated than just plain old sine theta. So I'm going to work on the left-hand side, right? So remember, what is tan again? Tan is sine over cosine, right? So I know that this is going to become what? Sine theta over cosine theta times cosine theta over 1 is equal to sine theta, right? Now, whenever we multiply fractions, we multiply straight across, crossing out the like terms, right? So now what do I have? I have sine theta is equal to sine theta. And that's it. I'm done. That's all this is. You make the left-hand side equal to right-hand side, and we're good to go. That's the end of the situation right there. Let's make a note. Let's make a note right here. All right, so this identity was fairly simple to verify. It only required writing tan theta in terms of sine theta and cosine theta. All right, very simple. Very simple. All right, let's look at another example then, shall we? A little bit more complicated. So verify the equivalency using the even odd identities. Verify the following equivalency using the even odd identities. All right. What I'm more interested in from all of you is just making the left hand side equal the right hand side, right? However you do it is however you do it. No pressure at all. All right, no pressure at all. So how I want to approach this now, sine of negative x, right? So if I put in a negative x value into sine, remember that sine is a what? It's an odd function, right? So that's going to become what? First part is fine, 1 plus sine of x. But the second part is going to become 1 minus sine of x, right? And that's equal to what? Cosine squared of x. Now, for me, cosine squared of x is the simpler side. So I'm going to work on the left-hand side, right? And all you have to do is just FOIL it, right? So 1 times 1, 1, 1 times negative sine x, sine x times 1 plus sine x. And last but not least, positive sine x times negative sine x will give me a negative sine x. Oh, sorry. Hold on. I made a mistake. A negative sine of x. And then, well, let me say sine squared of x. That sounds better. All right. And this is cosine squared x. Now, what do I want to do here? I want to combine like terms, right? So negative sine x and positive sine x kind of just, they cancel out, right? So now I have what? 1 minus sine squared x is equal to cosine squared x, right? Now check this out. If I add sine squared x over here, and what I do to one side, I have to do to the other. Sine squared x. Oh, baby. I have my identity. Cosine squared x plus sine squared x, right? And we know that cosine squared plus sine squared is equal to 1. So 1 equals 1. I'm done. That's it. So again, I want to make my left-hand side equal to my right-hand side. That's the goal here. That's the goal here. Okay. And no matter what I gets thrown at you, you can use that same identity to break down every single question. Right? Sines and cosines. Right? That's the trick. Sines and cosines. All right. So verifying trigonometric identity involving the secants squared. I don't care what it is. Break it down into sines and cosines. Right? So let's take a look at this. This is secant squared theta, right? Minus 1 over secant squared theta is equal to sine squared theta. Now, for me, sine squared theta is just simple. I'm just going to leave that alone, right? That's real nice. But for secant squared theta, right? We know that secant is what? 1 over cosine squared theta, right? So let's take a look at that. All right. So the sine squared theta, that's the simpler side. I'm just going to leave that alone. But the secant squared theta, just move this real quick. Sorry, I had a pop up. So the secant squared theta, remember that secant is what? 1 over cosine, right? 1 over cosine. So this is going to become what? 1, excuse me. Sorry about that. Sorry about that. This is going to become 1 over cosine squared theta minus 1, of course, divided by 1 over cosine squared theta. And then that's it, right? Let's simplify that. Now I want to simplify the numerator first, right? The top portion, right? So I have a fraction minus 1. So I'm just going to put another 1 underneath this so it could look like a fraction. Now I have a fraction minus a fraction, right? Remember, in order for me to subtract fractions, I have to have the same denominator, right? So this is going to become what? 1 minus cosine squared theta over cosine squared theta. And of course, that's all over 1 over cosine squared theta, right? Still equal to the sine squared theta. I'm just not going to write that again. So then now, what can I do? I can do keep, change, flip. So I could keep the numerator, 1 minus cosine squared theta over cosine squared theta. Change it to multiplication, flip the denominator, cosine squared theta all over 1 is equal to the same sine squared theta. And remember, what can I, what, now I have multiplication. These will cancel out. So now what am I left with? 1 minus cosine squared theta is equal to what? Sine squared theta. Let me add cosine squared theta over here. And what I do to one side, you know I have to do to the other, right? Add cosine squared theta. Oh, baby, right? I have what? Sine squared theta plus cosine squared theta. My identity. Sine squared plus cosine squared equals 1. So 1 equals 1. I'm done, right? As long as you get the left-hand side to equal the right-hand side, we're good to go. We're good to go. That's it. That's the name of this game. That is the name of this game right here. All right. Let's see what else we have. Now this is going to be a little bit more simple. Just a tad bit more simple. All right. So here we go. So this is creating and verifying an identity. We want to create an identity for the expression 2 tan theta secant theta by rewriting it strictly in terms of sine, right? Blah, blah, blah. Here's all I heard, right? You have 2 tan theta, right? Let me just I'm going to use a dot multiplication here, times secant theta, right? So what am I going to do? I'm just going to break this down. Just break it down the way you know how, right? You remember that 2 is not going to do anything, right? Tan is going to become what? Sine theta over cosine theta times what's secant again? 1 over cosine theta. Whoops. Try that again, right? Let's put a 1 underneath this 2. You already know what we're going to do, right? Multiply straight across. Multiply straight across. So what do I have? I have 2 sine theta over cosine squared theta. Done. That's it. Right? Can't complain about that. If I wanted to go a step further with this, right? Because they did say they wanted everything in terms of sine, right? All right, so let's please the question. Let's please the question, right? So what's my identity again? Sine squared theta plus cosine squared theta is equal to 1. Solve for sine squared theta. So I'm going to subtract cosine squared theta. What you do to one side, you know you have to do to the other, cosine squared theta. So now look at this. Sine squared theta is equal to 1 minus cosine squared theta, right? I'm sorry. Made a mistake there. Let me do some more math. I want to solve for cosine squared theta. I shouldn't have solved for sine squared theta. I'm going to subtract 1 from here. No biggie. Sine squared theta minus 1 equals negative cosine squared theta. Divide by negative 1, divide by negative 1. So I have 1 plus sine squared theta is equal to cosine squared theta. All right, boom. Plug that in. Now you have 2 sine theta over 1 plus sine squared theta. And there you go. Everything's simplified using just sine, right? Can't beat it. One formula that works for everything, right? That's the name of this game. That's the name of this game right here. All right, let's take a look at another one. These are kind of fun, right? Yeah, it's not too complicated, right? You see, we're only using one formula and just solving them all, right? Even though there's other instructions here, the one formula works for everything. We want to verify this. 1 minus cosine squared times 1 plus cotangent squared x is equal to 1, right? This looks a little complicated, but it's not, right? So look at this. I have 1 minus cosine squared x, right? Times 1 plus, what's cotangent again, right? Let me think about that. So cotangent I know is 1 over tan, and I know that tan is sine over cosine. So this is actually cosine squared theta over sine squared theta, right? Those parentheses is equal to 1, right? Can't beat that. Can't beat that, right? So let's work on the inside of that one real quick. So this is going to become 1 minus cosine squared x, right? Remember, in order for me to add two fractions, I have to have the same denominator. So this should become what? This should become sine squared x plus cosine. You know what? I don't. I'm so used to the theta. These should be x's. Sorry about that. Cosine squared x all over sine squared x is equal to 1, right? Now help me out, help me out. I can't remember this. Help me out, help me out. Sine squared x plus cosine squared x is equal to, let me guess, 1, right? So this is 1 minus cosine squared x times 1 over sine squared x. And I'm telling you, allegedly, that's equal to 1. Let's see if it does, all right? So what am I going to do here? Exactly what you think I'm going to do. Distribute. Keep it simple, not too complicated, right? So what does this become? 1 over sine squared x minus cosine squared x over sine squared x. Allegedly, that's equal to 1. Let's make it happen. Let's make it happen, right? I'm gonna put these together because that looks a little funny. So I have 1 minus cosine squared x over sine squared x is allegedly equal to 1, right? Oh baby. Let's see how we're gonna get through this one now. Right? It's a little complicated. A little complicated. So watch what I'm gonna do. I'm gonna multiply by sine squared x. And what I do to one side, I got to do to the other. Sine squared x, right? So now what do I have? I have 1 minus cosine squared x is equal to sine squared x. Now I'm going to add cosine squared x over here. What you do to one side, you know you have to do to the other. Add cosine squared x. What is this? 1 equals sine squared x plus cosine squared x. And remind, I can't remember. Sine squared x plus cosine squared x. What is that? 1 equals 1. I'm done. That's it. That's it. Same formula. Same formula. No change. All right? Very sweet. Very sweet. All right. Let's keep it moving. Let's keep it moving. All right. So using algebra, to simplify trigonometric expressions, right? So we have seen that algebra is very important in verifying trigonometric identities, but it is just as critical in simplifying trigonometric expressions before solving. Being familiar with the basic properties and formulas of algebra, such as the difference of squares, the perfect squares, or substitution, will simplify the work involved in the trigonometric expression and equation. For example, the equation sine x plus 1 times sine x minus 1 resembles the equation x plus 1 times x minus 1 equals 0, right? Which uses the factored form of the difference of squares. Using algebra makes finding a solution straightforward and familiar. We can set each factor equal to 0 and solve. This is one example of recognizing algebraic patterns in trigonometric expressions or equations. Another example is the difference of squares formula. A squared minus b squared is equal to a minus b times a plus b, which is widely used in many areas other than mathematics, such as engineering, architecture, and physics. We can also create our own identities by continually expanding an expression and making the appropriate substitutions. So using algebraic properties and formulas makes many trigonometric equations easier to understand and solve. All right. Now, I know you heard a lot just now, right? But just think through the problem, right? Think through the problem. No matter what problem I give you, you can always bring it back to the same formula and get through it. All right, let's take a look at this, right? So writing the trigonometric expression as an algebraic expression, write the following trigonometric expression as an algebraic expression, right? So what they're asking you to do, right? If I was to take cosine theta out of this, right? Take cosine theta out of this. I can assign a value to cosine theta. I'm going to call it x, cosine theta, right? Now, if I rewrite that equation, what do I have? I have 2x squared plus x minus 1. This looks nice. I can factor this, right? What does this become? 2x, x, right? I know this is going to be 1 and 1 because only two numbers that multiply to give you 1 are 1. But let's see, in the middle we have positives. That's positive. That's negative. I'm done. Now let's go a step further. Plug back in that cosine theta, right? So now what do I have? I have 2 cosine theta minus 1 times cosine theta plus 1. Bam. That's simple. That's all they're asking you to do right there. Hmm? Nothing big right there. Let's look at another example real quick, just for a second. Sometimes these tricks come in handy. So rewriting a trigonometric expression using a difference of squares. So let's take a look at this. I have 4 cosine squared x minus 1, right? Now, 4 cosine squared theta minus 1, excuse me, right? Same game as before. Same game as before. I'm going to pull out that cosine. I'm going to call it x, right? So cosine theta, pulling that out, this becomes what? 4x squared minus 1, right? Let's factor that. You already know this is the difference of two perfect squares right there. I have 2x, I have 2x, I have 1, and I have 1. 1 is positive, 1 is negative, done, right? After that, let's plug back in that cosine theta. This becomes what? 2 times cosine theta plus 1 times 2 times cosine theta minus 1. And that's it. That's it in a nutshell. Nice and simple. Easy peasy. All right? Can't complain about that. All right? Let's make a little note about that real quick so we take a look. So if this expression were written in the form of an equation set equal to 0, we could solve each factor using the zero factor property. We could also use substitution like we did in the previous problem and let cosine theta equals x, rewrite it as the expression 4x squared minus 1 and factor 2x minus 1, 2x plus 1, then replace x with cosine theta, which we did. And then you just solve for the angle if necessary, right? So solving for the angle means that it will be set to 0. You set both of them equal to 0, all that good stuff, right? Nothing crazy here. All right. Let's see what else we could get into here. I think this is pretty much it. Let's do one more problem just for fun, and then we'll call it at that. Here we go. Again, I don't really care how you guys do it. Make the left-hand side equal to the right-hand side, right? Even though they're giving me a hint, the hint is if you want to use it, use it. If you don't want to use it, don't use it. Make the left-hand side equal to the right-hand side, right? So I'm going to do this in my own way. I'm not even going to read whatever that hint says, right? You want me to verify it? I'm going to verify it, right? I see an equal sign. You know what pops into my head when I see an equal sign? Cross multiplication, right? So cosine theta times cosine theta right here. Boom, right? What is that? That's cosine squared theta, right? And then 1 plus sine theta times 1 minus sine theta, right? Boom. 1 plus sine theta times 1 minus sine theta. Easy, right? Foil that over. Let's look at what we have. I'm just going to put an equal sign just to keep it simple, right? 1 times 1 is 1. 1 sine, this is negative sine theta. Positive sine theta times 1, this is positive sine theta. Last but not least, positive sine theta times negative sine theta will give you a negative sine theta squared, right? So negative sine squared theta. Combine like terms, these cancel out in the middle. What do I have? I have 1 minus sine squared theta is equal to what? Cosine squared theta. Watch what I'm going to do. Add sine squared theta over here. Add sine squared theta over here. Keep it going, right? So cosine squared theta plus sine squared theta is equal to 1. You know my identity. Cosine squared plus sine squared, 1 equals 1. I'm done. That's it. Nice and simple. All right. Knock out your homework for this, and we'll keep it moving from there. All right, y'all.